Okay, so I think, of course, there is a gap of about 14 days now to our last class. We were looking at these four machines. Again, I'm stressing you the fact that this is a very important slide for the computer science students, right? So there are four kind of machines, four kind of languages that they accept, and four kind of grammars. Each language has a grammar, right? So we already talked about finite automata. We talked about deterministic finite automata and non-deterministic finite automata. We talked about push down automata, PDA, and we talked about briefly we talked about linear bounded automata, and we talked about Turing machine. Okay, so in fact we talked about all these four machines. Today is the last lecture in this series, where we are going to talk about, you know, a universal Turing machine. So the main purpose of today's lecture is that I will show you that there are languages which Turing machine cannot accept, basically, and the proof is based on a nice mathematical uh, topic known as countable uncountable. So essentially, I will show that there are, know of course, there are infinitely many Turing machines possible, but there are more languages than the number of Turing machines. Okay, so obviously there are if there are more languages than the number of Turing machines, in that case there will be certain language for which there is no Turing machine which can accept. Right, so that means there is a Turing barrier. There are certain problems which Turing machine cannot solve or cannot accept. Okay, that is the key philosophy. So first, I'm going to talk about universal Turing machine, and then I will talk about countable and countable, and then using that trick I will show you that number of Turing machines are countable, whereas the languages are uncountable. Okay, that is a thing. So what is a universal Turing machine? So again, I'm thankful to Professor Busch. I'm using his slides with permission. So this is the last slide from his lecture that I'm going to use. Okay, so a limitation of Turing machine is that Turing machines are hardwired. They execute only one program, whereas real computers are reprogrammable. So how do we solve this problem? So actually, I can define what is known as universal Turing machine. Okay, so universal Turing machines are reprogrammable machines and simulates any other Turing machine. So how do we do that? So actually, I am going to use a Turing machine with 3 tapes. So given a Turing machine, I can simulate it on this universal Turing machine, which consists of 3 tapes. Each tape, so basically, as you know that there are Turing machines with multiple tapes, that is a possibility in the variation of Turing machines we saw. So we can use that kind of machine to simulate any other Turing machine. How do we do that? Each Turing machine is mapped into the string of 0 and 1. Okay, and that you can simulate. So how? So basically, so universal Turing machine simulates any other Turing machine. So input of universal Turing machine is descriptions of transitions of M and input a string of M. So here here are 3 tapes. Tape 1 uses description of machine. Okay, so universal Turing machine has 3 tapes. One tape description of M, tape content of M is on another tape, and state of M is on the another tape. So these 3 tapes can simulate the Turing machine. So let me describe in detail how do we do this. We describe Turing machine M as a string of symbols. Okay, so we encode machine M as a string of symbols. So first I need alphabet encoding. Okay, so suppose symbols are A, B, C, D. These are the alphabets. So I use them. A as 1, B as 2 ones, C as 3 ones, D as 4 ones, and so on. Right. So like this, I can describe alphabet encoding. Next, I need to talk about state encoding. Right. Similarly, there could be a bunch of states, right? So each state I will encode as again ones, unary encoding. Q1 as 1, Q2 as 2 ones, Q3 as 3 ones, Q4 as 4 ones, Q5 as 5 ones, and so on. Then I need to also talk about head movement. You know that the normally Turing machine, the head can move into the left or right. So left is encoded by 1, and right is encoded by 2 ones. Okay, so you can see that we are using this same number of ones to describe different things, but then that means we require some sort of separator in between. Okay, so here is for transition encoding. How do we do this? Suppose we are in state q1. After input a, we arrive at state q2. Okay, and replace a with b and move left, right. So this can be encoded as q1 as 1, as you saw. Then there is an alphabet. So now alphabet a is 1, but then there is a separator is used here. You see, 0 is a separator here, another separator here, another separator here, another separator here. So all the other things we can encode. So essentially, so this transition can be encoded as a binary string of 0 and 1, right? So two different transitions, if suppose you want to use on the same tape, so then we use another separator with 2 zeros. Okay, so here these are separators of the single zero, single zero, single zero, single zero, single zero, single zero, single zero. But then here we can use a separator of 2 zeros. Okay, so this is also a way to encode two transitions. So that means tape 1 contents of universal Turing machine. So it's a binary encoding of the simulated Turing machine. Tape 1 will have something like this, right? 1 0 1 0 1 and so on. So everything is encoded here, right? Because essentially given a Turing machine, your ultimate task is to encode all the uh, basically transitions. Okay, if you can capture the transitions, you essentially capture the whole machine, because you know how to simulate. So a Turing machine is described with binary strings of zeros and ones. So that means given a Turing machine, it can be described with binary strings of 0 and 1. So therefore the set of Turing machine forms a language, right? Because any Turing machine can be you take any Turing machine, arbitrary Turing machine, it is nothing but a binary string, right? If you look at all Turing machines possible, they are a collection of binary strings, and you know that collection of binary strings forms a language. Each string of this language is a binary encoding of a Turing machine. So therefore the set of Turing machine forms a language. Now I can show that this language is countable. So set of all Turing machine is countable. I'll tell you what you mean by countable. It means we can count. You know, I'll pick up the first machine, the first binary string. I'll say 1. This is machine number 1. Then next machine number 2. Then next machine number 3, and so on. There is assignment with a set of natural numbers. So we say that it is countable. Let me show you in details. Okay, so this is the language of Turing machine 1, you know, described by say some language, Turing machine 2 by another language, Turing machine 3 by another language, and so on. So the collection of all Turing machines forms a language. Okay, this is a very important observation. So Turing machine can be described with bunch of binary strings, and the collection of all Turing machine forms a language. Okay, now I am going to describe what is known as countable set and uncountable set. So what do you mean by countable set? You know, if I say write down say 4 6 9 11 5, this set. So this set is countable or uncountable? Of course there is only finite many elements, so this is countable, right? I can count all the elements. How many of them are there? 1 2 3 4 5. There are 5 of them, right? So so this is a finite set. Finite set, there is no problem, right? Finite set, no problem. Less than infinity, right? We can count. If the set is infinite, say for example, if I have 2 4 6, okay, 8 10 and so on, this is a finite set of even numbers, you can say that, right? And if I ask a question, is this set of even numbers countable or uncountable? So basically I am going to assign it each number. So basically if I have to count, I say I pick up 2, I say 1 2 3 4 5 and so on. So essentially I am doing an assignment with 1 2 3 4 5, right? So there is some sort of one-to-one correspondence with set of natural numbers, right? There is one-to-one correspondence with set of natural numbers. So this is set of even numbers and set of natural numbers. right? So there is a one-to-one correspondence. So this correspondence is given by f of n is equal to 2n, right? So if you put, so basically if I take 2, I can say 1, 4, I can say 2, 6, I will say 3, and so on, right? So this function is from natural numbers to even numbers. If there is a one-to-one and onto function between these two sets, then we say that set of even numbers is countable. So basically a set is countable if it is finite, or if it is infinite, we say that a set is countable if there is a one-to-one correspondence with a set of natural numbers. Okay, so in this case set of even numbers is countable. So infinite sets are either countable or uncountable, of two kind. Okay. So as I said, countable set means there is a one-to-one correspondence of elements of the set to natural numbers, positive integers. So every element of the set is mapped to a number such that no two elements are mapped to the same number. There is a one-to-one correspondence. As I told you, the set of even integers is countable, right? So here if I include 0 as well in the even integers, so now you can see that the mapping is 2n to n plus 1, right? This mapping will work. Okay, so this is a one-to-one correspondence. This is a function which is one-to-one and onto. That means this set of even numbers is countable. Now what about set of rational numbers? Any idea? Set of rational numbers, are they countable or uncountable? Can I count them? Yes. Anyone can unmute and answer. Set of rational numbers, like numbers of the form p by q, right? 1 by
Well,
2.
I think that we can count them because we can write numerator as a sequence of integers and also denominator as a set of integers.
Well, the answer is yes, we can count, but
We
actually,
can.
you need to find a map which is one-to-one and onto. Anyway, let me give you a sort of a approach, and I will leave as a T exercise for you to find out the map. Okay, let me show you. So one thing is that, okay, nominator, denominator, okay. So naive approach is if 1 by 1, 1 by 2, 1 by 3, the correspondence is 1, 2, 3. But this does not work because we will never count 2 by 1, 2 by 2, 2 by 3, right? So this does not work. Better approach is you write down. So basically I am writing, suppose all the positive ones first. 1 by 1, 1 by 2, 1 by 3, 1 by 4, 2 by 1, 2 by 2, 2 by 3, 2 by 4, 3 by 1, 3 by 2, 3 by 3, 3 by 4, 3 by 5, and so on, 4 by 1, and so on. Like that you write down all positive ones. Okay. Now how do I count? First 1, so 1, 2, so I'll say that 1, 2, 3, 4, 5, and like this we can count, right? First I have count this, then this, then this, then this. Now you see that these are the numbers of the same height. So the height of this number is 1 plus 1, numerator plus denominator. This is 2. The height of these two numbers is same. 2 plus 1, 3, 2 plus 1, 3. Height of these three numbers is same. 3 plus 1, 4, 2 plus 2, 4, 3, 3 plus 1, 4, right? So like that, first you count numbers of height 2, then you count numbers of height 3, then you count numbers of height 4, then you count numbers of height 5, and so on, right? So now this correspondence is going to work, right? This will count all the positive rational numbers excluding 0. Now so basically if you want the negative ones, so you can insert negative ones in between here. Okay, and the same mechanism will work. So my question is, a set of rational numbers is defined by p by q, right? So that q is not equal to 0 and p and q are integers, right? You have to find a map f from set of natural numbers to set of rational numbers, which is 1 to 1 and on 2. Find this map. Find f. This is a T problem for you. Okay, in the evening, sit down with a cup of tea or coffee and see if you can find this function which is 1 to 1 on 2 from set of natural numbers to rational numbers. So in this example here, you know that 1 corresponds to 1 by 1, 2 corresponds to 1 by 2, 3 corresponds to 2 by 1, 4 corresponds to 1 by 3, 5 corresponds to 2 by 2, and so on, right? So like this, so this is the correspondence we can do. I want you to give me a formula for this, including the negative ones as well, right? Because negative ones I have not counted here, right? So you have to include the negative ones as well. And of course, when p is equal to 0, that will also work. So basically 0 you can put somewhere here, the negative ones in between, you start with 0 and then you count everything. So basically the systematic idea how to count, but the map you need to find out. Okay, so this is a challenge for you, this is an exercise for you. Just try to find out a map which is one to one and onto from the set of natural numbers to set of rational numbers. Okay, this is an important thing. So set of rational numbers are countable. Any question at this point?
Sir, I had a question. Sir, means that this means that if we are having some numbers that are discrete, but we cannot find a map, means we cannot, means which are not related, means which are not in a particular sequence, then we cannot say that it is countable.
So the thing is that a set is countable if, number one, either it is finite, then no problem, right? Finite set you can always count, right?
Yes, yes, yes,
Now,
yes.
if the number of elements in the set is infinite, then you have to find a one-to-one and onto map from set of natural numbers to that set. Okay, unless you find that map, you cannot say it is countable. In this example here, I can show you that the set of rational numbers are countable because I am showing you the way how to count, right? So essentially,
Yes.
yeah, I am telling you, but of course you need to find an explicit formula for that. That I have left as an exercise for you, but otherwise
Okay.
you know how to count, right? So essentially
Means
what I'm saying that you give me in one number from the set, I will say 1. You give me another number from the set, I will say 2. You give me another number from the set, I will say 3, and so on, right? There should be one-to-one correspondence. And you should understand that we should be able to cover everything. So in this example, the way it is done, we know that everything will be covered, nothing will be left, right? So the set of rational numbers is countable.
Means if there is a set for which we cannot find a formula that maps
Yeah,
that
no,
maps
yeah.
from.
If there is no, it's not about formula. If you cannot find a one-to-one and onto function, okay,
Okay, yes,
so
yes,
so then
okay.
we say that the set is uncountable. Okay.
Okay, means formula is not necessary condition for countability.
Yeah. Map is necessary. In fact,
Yes,
that
yes.
map is going to tell you what is the formula, right?
Oh,
Mm,
yes, 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 sir. Understood, understood, sir. Understood, sir.
mm.
Thank you, sir.
Thank you. So, set of rational numbers is countable, right? Because we have described enumeration procedure or enumerator, right? I told you how to enumerate them for the correspondence to natural numbers. So now these enumerators are very, very important. Now actually I can show you that set of all Turing machine is countable. Now any idea how do we do that? Set of all Turing machines, so Turing machines, each Turing machine corresponds to a binary string, right? Now how do we count them? And something that is pretty easy is actually you somehow, because each string has some length, right? It will be some length, right? So I can map somehow length to the set of natural numbers, and that's the way I can establish a one-to-one correspondence or enumerator for the Turing machine. That's a key idea I'm going to describe in the next few slides. So let S be a set of strings language. An enumerator for S is a Turing machine that generates, prints on the tape all the strings of S one by one, and each string is generated in finite time. So let me describe. So strings are S1, S2, S3. Enumerator machine for S is a output on tape, so S1, S2, S3, and in finite time, T1, T2, T3, and so on. So enumerator machine configuration is this: in time T1, you print, S1 on the machine. In time T2, you print S2 on the machine. In time T3, you print S3 on the machine, right? So observation is, if for a set S there is an enumerator, then the set is countable. The enumerator describes the correspondence of S to natural numbers, okay? Now the set of strings ABC plus is countable. So let me show you an example. Set of all strings of our alphabet ABC, where of course empty is not there, is countable. So we can describe an enumerator for S. So if you produce the strings in lexicographic order like A, right? 3 times A, 4 times A, and so on. This does not work because strings starting with B will never be produced. So what we can do, the proper order is produce all strings of length 1, then all strings of length 2, all strings of length 3, all strings of length 4. This looks like a correspondence with set of natural numbers, a canonical order, right? Okay, and this is going to work. Length 1 is strings, length 2 is strings, length 3 is strings. This is the proper order. So there is an enumeration now. I can enumerate, and so this set is countable actually. So now similar technique shows that set of all Turing machines is countable. Okay. So any Turing machine can be encoded with the binary strings of zeros and one. So find an enumeration procedure for the set of Turing machine strings, right? So how do we enumerator is generate the next binary string of 0 and 1 in proper order, in this increasing length. Check if the string describes the Turing machine. If yes, print the string on the output tape. If no, ignore the string. So this procedure counts the number of Turing machines, right? Okay. So binary strings and the Turing machines. So this shows that set of all Turing machines is countable. Okay. Set of all Turing machines is countable. This is something very important. That means no matter what kind of Turing machine you construct, they come from a fixed set which is countable. Okay. Now I am going to
Hello,
talk
sir.
about, yes.
Sir, in that set of all Turing machines are countable. When we separate them by length, then how it will be one-to-one mapping?
No. So we are describing an enumerator here. You see, this is the procedure. Generate the next binary string of 0 and 1 in proper order. Check if the string describes the Turing machine. If yes, print the string on the output. If no, ignore the string. So this procedure is enumerator. See, so I am saying that I'm not giving you the explicit function one-to-one and on-to function, but what I'm giving you enumerator. Just like in the case of rational numbers, right? I give you enumerator. Okay.
Okay.
Yeah.
Thank you, sir.
Okay, so now we talk about uncountable sets. This is something beautiful, and I think just pay attention here about uncountable sets. So as I told you, so set of all Turing machine is countable. We will prove that there is a language L prime which is not acceptable by any Turing machine. And how do we do that? I will show you that. Of course, I have shown you to that Turing machines are countable, but languages are uncountable. This is very important. So that means there are more languages than Turing machines, right? This is the key trick. If there are more languages than the number of Turing machines, obviously there will be some language which cannot be accepted by the Turing machine, right? Right. So that's how we can say that there are problems for which Turing machine cannot handle. Okay. Now, so a set is uncountable if it is not countable, right? So that means if we cannot describe a enumeration procedure, or if we cannot find a one-to-one and on-to function, we will prove that there is a language which is not acceptable by any Turing machine, as I told you. Now, let me show you a very nice example. I mean, this theorem actually, and the proof is based on a very nice Cantor diagonalization argument. If S is an infinite countable set, S is an infinite countable set, then the power set of S is uncountable. Okay, what it is saying? If S is a set which is infinite and countable, okay, if S is a set which is infinite and countable, then the power set of S is uncountable. It's a very beautiful result, and let me show you how do we prove this. Its proof is very important, based on Cantor diagonalization argument. Okay, so okay, so the let me show you the proof, and we will use this theorem here to show that there are more languages than the number of Turing machines. Suppose S is countable, right? So what we are going to do now, I think just pay attention, be careful now. It's a very little bit tricky argument. That's why just pay attention. Suppose that S is countable, right? Since S is countable, right? I mean, it is given to us that S is infinite countable set, right? S is infinite countable set. Suppose S is countable, so we can write elements of S as S1, S2, S3, right? And these are elements of S, right? You can see that this is the first element, second element, third element, fourth element, and so on. Now, elements of the power set will be phi, say S1, S3, as some combination of elements of S, right? Now, note that each of these power set can be described by a binary string, right? How? We encode each element of the power set with the binary strings of 0 and 1. So S1 power set element is S1. So S1 is there and rest are absent. So rest of the place I will put 0. So this is described by the string 1 0 0 0. If the element is S2 and S3 in the power set, so I am describing it S2 and S3 as 1 and rest of things places it is 0. If the element is S1 S3 S4, so S1 S3 S4 is 1 1 1, rest of the places it is 0. Okay, so that means every element of the power set can be described by a binary string. Agreed? You can answer agreed.
Yes.
Yes, sir.
Yes, sir.
Okay, good. Now, observation is every infinite binary string corresponds to an element of the power set. And the reverse way it is also true, right? If you take a binary string, something like this, so this is S1, S2, S3, S4, S5, S6, and 0, right? So every binary string will also correspond to some element of the power set, right? This is also possible, right? Fine. Now the trick of the actually proof. Let us assume. So I have to show that the power set is uncountable, right? The power set 2 raised to power S is uncountable. S is a countable set. I have to show that the power set is uncountable. Suppose that the power set is countable. I am assuming a contradiction. I am saying suppose it is countable. Then what will happen? Once we assume that the power set is countable, in that case we can enumerate the elements of the power set by say T1, T2, T3 and so on. The first element, second element, third element, fourth element of the power set are countable, right? Now power set elements, so T1, so there could be a binary, and we know that every power set element has a binary encoding, right? So suppose this is the binary string, some binary string, I don't care where is a 1, where is a 0. T2 is another one with this binary string. T3 is another one with this binary string. T4 is another one, this binary string, right? So each element of the power set corresponds to a binary string, right? F0 and 1. Okay, got it? Now we have assumed that the power set is countable, right? We have assumed that the power set is countable. Okay. Now I am going to produce a string. I am going to produce a string which is not in this set. This is very, very important. Look at it carefully. Take the binary string. Take the binary string whose bits are the complement of the diagonal element. I am constructing a binary string T, which has first element 0, which is complement of first diagonal element. The 1, I should take 0. The second string is 0 here, which is complement of 1, which is 0 here. The complement of 0 is 1 here, and complement of this 0 is 1 here, right? So this is how I construct a string, right? Now what will happen, right? This string will never come in this set that we are doing it. Do you agree or not? This T will not be equal to Ti for some I. So I am saying that T, this binary string will not equal to Ti for some I. Do you know why? Because if for the ith entry it is equal, in that case, this complement thing will be a problem, because the ith entry here will be the complement, so it will never be equal. So basically you see that T, the fourth entry is a complement here, right? Third entry is complement here, second entry is complement here, and the first entry is complement here. So the way we have constructed this, okay, this element, this string T, it will never be in the set, right? Do you agree or not? I think I would like to hear some of your comments.
Yes, sir. Yes, sir. Agreed to.
Yes, you agree, right? So this T, which I am trying to construct, which is I am trying to construct using the complement of the diagonal element. So this T will not be equal to Ti for any I, right? So this T will never be in the set. Now I have said that this power set is countable. I am listed all of them T1, T2, T3, but then I am able to find a T which is not in the set. That means our assumption is wrong, right? That means this is not a proper enumeration, right? So that binary string, this we know that this binary string, whatever we have constructed T, will correspond to some element in the power set, right? But this is not in the set, which is a contradiction. So thus T must be equal to Ti for some I. However, the ith bit in the encoding of T is the complement of the ith bit of Ti. Thus T is not equal to Ti. This is a contradiction, right? So I was able to produce a element T which is never in the set, which is in the which is element of the power set, but which is not in the enumeration procedure. That means that our power set is uncountable. Our assumption that the power set is countable is wrong. That means the power set is uncountable. Okay, so that's the result. So that means we are able to describe that if S is an infinite countable set, then the power set of S is uncountable. Any question at this point? Because I know that sometimes it is tricky to understand. If there is any question, I can repeat it. Anyone can ask. Any question in this construction business? So key idea was here. This was the key slide, right?
Hello, sir. I don't understand this. Means how it will not come in any set.
So I have
This
said that
complement.
suppose the power set of S is countable, right? And so the elements are T1, T2, T3, T4, and so on, T5, and so on. We can keep on writing like this. Each Ti will correspond to a binary string, right? Some binary string. I have written some binary string here. Okay. Now I am producing a string T, which is the construction of T is such that each entry here is the complement. The first entry is complement of the first diagonal element, second entry is complement of the second diagonal element, third entry is complement of the third diagonal element, fourth entry is complement of the fourth diagonal element, and so on. Fifth will be complement of the fifth string, whatever it is, right? So this T will never be in this collection of Ti's, right? But this corresponds to a element of the power set. T should be equal to Ti for some I, but the way we have constructed T will never be equal to Ti for any I, and hence there is a contradiction. Got it?
Yes, sir.
Hmm.
Okay, thank you, sir.
So the power set is uncountable, right? Since we have a contradiction, the power set of S is uncountable. So if S is a countable set, its power set is uncountable, and we have used the principle what is known as Cantor diagonalization argument. So now, just to practice this, I would like to ask you T time problem. Show that real numbers are uncountable. Okay, real numbers are uncountable, or you can say that all entries, all close interval between 0 and 1, this set such that 0 is less than equal to x is less than equal to 1 is uncountable. Okay, and the technique is simpler. So suppose you want to show the real numbers are uncountable, write down every element, every real number as a decimal expansion, right? And those decimal expansions, you have to suppose it is countable, write down the first real number is r1 is some decimal expansion, r2 another decimal expansion, r3 another decimal expansion, and so on, and then you produce a real number r which is sort of complement. Now here are the complement. So whatever entry is coming, if suppose the first entry r1 is, I'm assuming that it is 0 point, suppose I'm doing assuming that it's the decimal expansion, this portion I am leaving. I mean, if you want you can keep that. So it is r1 prime, r2 prime, r3 prime, and so on, right? And then r2 is 0 point, r2 2, r2 2, r2, sorry, r1, r2, r3, something like that, So now you see that once you choose a real number r, which is other than this element anything from 0 to 9, So if this element is say 1, you can take anything other than 1. If this element is 3, you can take anything from 0 to 9 other than 3, and then you produce this element R, so which will never be in the set. This is how you proceed. Okay, I just gave you the sketch how to proceed to show that the real numbers are uncountable. Okay, so this proof you should do it at home. It's a key problem for you. Okay, so now we can apply this thing to the languages. If the language is AB, the set of all binary strings, set of all strings, these are infinite and countable, so we can enumerate the strings in proper order. Okay, and any language is a subset of S, fine. The power set of S contains all languages, which is uncountable, right? This is a nice thing. It's application of the language. Now we look at the Turing machine business. Alphabet is AB, Turing machines countable, and they accept languages described by Turing machines L1, L2, L3. So Turing machines are countable. This is countable. If denote X is this, so the power set X is a subset of power set of S, right? So all possible languages are uncountable, right? And the Turing machines are countable, and hence there are basically more languages than the number of Turing machines. I think so. That's a key idea about today's lecture. Okay. So there is a language. Conclusion is there is a language L prime not accepted by any Turing machine. There is a language X in the power set. Okay, for which there is no Turing machine. Cannot be described by any algorithm. Okay, so that means there is a Turing barrier. Okay, so not everything can be solved by Turing machine. So that's all for today's class. Actually, I think this was a very important lecture. This showed to you. So that means I told you about everything about Turing machine. Okay. So I think this portion is done. I think in the assignments I have given you, to do certain calculations with Turing machine, say addition, subtraction. So addition you have already seen. Subtraction you can design a Turing machine, or multiplying two numbers, and so on. And I think that's all. So in the next class, I'm not going to start it today, but in the next class, okay, I'm going to talk about matrices. That's our next lecture. So I think most of the theoretical computer science we have covered. This much is enough for you in the beginning. If you want to know more about these things, so of course I should mention to you, there is a nice book by Sipser, Michael Sipser, Introduction to Theoretical Computer Science, and also there is a book by Automata, and this book by Rajiv Motwani. I think I don't know if any of you know Rajiv Motwani. Rajiv Motwani was the person who was a mentor for Google, actually. So the Sergey Brin and Larry Page, they did their project with Rajiv Motwani actually when the Google was born. And he helped initially Google company. He was a professor at Stanford. He was an Indian who did BTech from IIT Kanpur, and then he did masters and PhD from US, and he was a professor at Stanford, and he died due to a heart attack some time ago. But I think his wife is running a company which helps startups, to so you can actually still get those kind of help from that family. Anyway, so I think that's all. Any question at this point about all this, whatever we have covered in this area about these four machines? So this is a very, very important topic. Okay, that these four machines are very, very important. Their relationship is very, very important. I have not talked about many other things, like why some languages cannot be accepted by some machines and so on. So those are, for example, they involve what is known as pumping lemma and so on. I have not covered any of those things. So once you do a full course on theoretical computer science, you can look at those things. But if you want, you can look at either of the book by Motwani or Michael Sipser. Okay, both are very good books. Motwani book is pretty nice. I liked Motwani book. Sipser book is also very good. Sipser book is from MIT Press. Okay, so I think these two books you can look at it if you want to read more about it. Of course, there are many books on Introduction to Theoretical Computer Science. You can find more lectures and a lot of applications of these things in real life. Okay, because this is the fundamental thing to computer science. Okay, so if you have any question, I will wait for you, otherwise we can close the session. Any question, please ask.
Sir,
Yes.
sir, in that the diagonal which we took the complement
Yes, yes.
in that it is giving a another unique which is not belonging to the set, because at max from that set, if a T1 is of length n, then at max we can only have n minus 1 elements of
No,
some
it's not.
Ti.
It's not about length. Actually, it's not about length. You see what is happening here. Uh, so what I am doing, I have assumed that all of them are countable, right? Power set is countable. So I'm writing T1, T2, T3, T4, T5, T6, T7, T8. You can keep on writing it, right? For any I, right? Now everything has a binary representation, right? So I'm just worrying about, I don't know whether it is 1 or 0. I don't worry about that. But if it is 0, I will take construct a T which is the complement of this. If it is 0, I will take it here 1. If it is 1, I'm taking it here 0. Like that, every diagonal thing I am taking as a complement, right? So it has nothing to do with length here. So what is happening now? This T will never be in the set, because if it is equal to Ti, then it differ at the ith bit will differ, right? So it will never be equal to the Ti. So that's why the contradiction is there. Okay.
Yes, yes.
Hmm. Okay. Any more questions?
Hello, sir.
Yes.
Sir, why is natural numbers are counted?
Why?
Oh, hello, sir. Am I audible?
Yeah. Please tell me.
Sir, why is natural numbers are countable?
Natural numbers are countable by definition. In fact, what I am saying that something is countable if I give you a collection of things from the natural numbers. Okay, you can count. You pick up the first one, it is countable. You first one, second one, third one, fourth one. You can keep on picking up the numbers from the set, right? So there is a one-to-one correspondence with set of natural numbers anyway. The function f from n to n is always one-to-one and onto, right? It's the same set, right? It's a trivial thing. So a set of natural numbers are countable anyway, right?
Yes.
Sir, I had a doubt.
And
Yes.
Sir, means I didn't understand why there are more languages than Turing machine, because to each Turing machine we can correspond a language which it accepts, right?
Right. So the set of Turing machine is countable.
So the set of languages is also countable, right?
No. So the set of so what I'm saying, there are more languages. The power set of that thing will be more, right? Power set. We are looking at the power set of the languages,
Power set. So it
right?
means that power set is
Power
also
set of a
considered.
countable set. We are looking at power set of a countable set, which is always uncountable.
Yes, sir, that is uncountable.
Yes. So that's the thing.
Okay, means we are looking at a universal Turing machine, and as that power set is uncountable, means we cannot make a Turing machine from that argument that it accepts all the
So there
languages.
are more languages than the number of Turing machines. So what I'm saying that if a set is if the set of Turing machine is countable, right?
Yes.
And the power set is uncountable. Just now we show you, right?
Yes,
If I say
I understood that power set is uncountable, but how
so,
will
there are
it?
more. Essentially, power set also contains strings only, right?
Yes.
Yeah. So it's a language. Huh? So what I'm saying that basically there are more languages than the number of Turing machines.
hello, sir.
To each Turing machine, we can correspond a language.
Each Turing machine corresponds to a binary string, which is a part of the language, right?
Yes, but I didn't
Language
understand
is
that
what? What is language? Language is collection of strings,
collections of strings. Yes.
right? and that's why, because each Turing machine corresponds to a binary string. So if you look at all Turing machines, they are countable. I have shown to you that all Turing machines are countable.
That I understood that Turing machines are countable. But I didn't understand that why there are more languages than the Turing machines. I didn't
Because the
understand.
power set is uncountable. If a set is countable and its power set is uncountable, then there are more languages, right?
Okay.
Think about it if you still don't understand,
Yes.
right?
Okay.
Sir, can you give some examples of language which are not acceptable by Turing machine?
In fact, there are different kind of problems. For example, halting problems. But I think that I would say that at the present moment, it is outside of your course right now. But of course, the halting problem is we cannot solve. Okay. So there are things which I think look into the actual course. Okay.
And
Yeah, because we have to cover more things then. Whatever I gave you in this total computer science is the gist of the subject, the basics. Okay, I have not gone into many details. I have not talked about many things. Even you can apply these things through the compiler constructions and so on. Okay, parsers can be designed and so on. All those things I have not touched.
and sir, set of natural numbers is infinite, but we say it countable finite.
Which one?
Countable infinite set of natural numbers.
Set of natural numbers are by definition they are countable, right? Because that is a reference point. See,
Yes, but set of natural numbers, it has infinite number of elements, right?
right.
And set of real numbers also has infinite number of elements.
Correct.
But we say set of natural numbers is countable infinite set, and set of real numbers uncountable infinite set,
Correct.
right?
Correct. Yes.
So the complex number is also infinite, means infinite number of elements.
Complex
Is
numbers.
there
Yes.
any another term for complex numbers?
No.
Infinite,
So I am saying that now you can talk about whether the complex numbers are countable or uncountable or not. Whether they are countable or they are uncountable.
uncountable.
Yeah. So for all these things you need to prove. Okay. So I gave you an idea how to show that the real numbers are uncountable. The same Cantor diagonalization idea will work actually. Okay. So Cantor diagonalization idea is going to work where we are writing the decimal expansions in the real numbers case, and then we are enumerating procedure, and then we are producing a real number which is not in that set. The same idea which I gave you for binary strings, the similar idea work for the real number decimal expansions. So I think I have given you as an exercise also in the in the assignment. So you can look at it and try to show that the real numbers are uncountable. Okay.
And
So
sir, set of irrational numbers are countable or uncountable?
yeah. So now that's a good question. Now think about it. Whether a set of irrational numbers are countable or uncountable. Can you find a enumeration procedure? If yes, then it is countable. So I'm not giving you a firm answer here, but I would like you to explore and see. Okay. So there are, I think there are many sets